Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to help you out with one of these Gauss's law problems. So let's see, insulating sphere with a radius A has a minus q charge distributed uniformly throughout its volume. Then there's a conducting shell around it in a radius B and C, outer radius C. So again, radii, there's your A, B, C. Let's see what our first question is here. Oh, I guess it's just the one question there, right? Use Gauss's law to find E at R equals 3/4 R. Oh boy, I see that's not worded quite like I wanted. I'm sure what I meant by that, by the way, I'll change this, is 3/4 A. So what that means is, when we're looking here, we're talking about like 3/4 of the way out. That's what I meant. Like if I put a dot, like probably right about there. And what you want to do, all right, if we're going to use Gauss's law, is you start by drawing a Gaussian surface. And I like to draw my Gaussian surfaces in green. So the Gaussian surface might look something like this. Now, some other little tidbits here. It says something about the sphere, let's see, has a conducting shell with a plus 2q on it. So this shell is charged. Plus 2q. That's the net charge on it. And I'll talk about that a little bit later. I'm not going to worry about that right now. Right? So you draw your Gaussian surface, where this radius right here is the 3/4 R. Then you write out Gauss's law, which is the total flux, right, which is the integral E dot dA over the entire surface is equal to 4 pi k times the charge inside the surface. Now, when you deal with Gauss's law, usually you got to figure out this, the dot product part. Remember, the dA vector, right, has a magnitude of area, and it's in the normal direction. So draw a couple normal vectors on your Gaussian surface. I'll go ahead and draw one of them for you. All right, maybe here's one right here. Normal vectors always have to make a right angle to the surface, and outward is the positive direction for that. Do not worry about the fact that there's negative charge in there. That doesn't have anything to do with the direction of the normal vector. Next, ask yourself right at this point right here, what is the electric field direction at that point? And I'll give you a hint here. It's either inward or outward. I'll let you decide. And then maybe draw normal, maybe here and here, and electric field vectors at those same places. And you should be able to come to a conclusion about the angle between the electric field and the normal everywhere on that Gaussian surface. And that's going to allow you to figure out the dot product part. Then ask yourself, is the electric field like here, here, here going to be the same? Right? If I'm 3/4 of the way out symmetrically. And then, once you answer that question, that should tell you whether this is constant on the integral and whether it can come out in front or not. So that's basically, hopefully, enough to get you the left-hand side of this. Let me talk about the right-hand side now, the charge inside the surface. So that's this stuff. And the charge inside of there is going to equal the charge density. I usually denote that with the Greek letter rho, times, I'll put volume of the GS here, times the volume of the Gaussian surface. So figure out, write down something for the charge density. Now keep in mind that total charge we only need the magnitude here. The total charge Q is spread out through this entire volume. That will give you the charge density. And then multiply by the volume of your Gaussian surface. So that should hopefully be enough to get you to the point where you can find the electric field at that point. Now, one thing you might notice is, well, what about this stuff? And I would say, what about it? Gauss's law, remember, is only about charge inside the surfaces. Charge outside the surfaces don't have anything to do with what's happening at the Gaussian surface or inside of it. So honestly, just won't come into play. So there may be more questions about this later on, or it will, but for the question asked, it just isn't part of it at all. That probably will show up maybe later in the problem, but for 29, that's about it. Anyway, I hope that this helps. Have a great day.